Welcome everyone to the 2022 Vision Spectra Conference. Thank you all so much for joining us. And in this session, you will hear from Austin O'Neill, a senior member of Metaphase Technologies Applications Engineering team. Austin is A3 certified vision professional with more than 5 years of experience in machine vision. Today's talk will feature lighting considerations for line scan imaging. If you have any questions or comments, you can type them right into the conference chat box on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. If you have any technical issues throughout the event, please log out and back in to rejoin the session. Lastly, Austin, thank you so much for taking the time to present here at the 2022 Vision Spectra Conference.
All right. Thanks, Jacob. And again, I'd like to thank everyone for attending today. I'm excited to be able to talk to you about the line scan applications and lighting and the similarities between area and line. Like I said, I'm Austin O'Neill, and let's get started. So just as a housekeeping, we're going to be going over the differences between an area and line scan system, the similarities and differences that they share, and how we can go from our understanding in an area scan environment to one that is line scan based. We're also going to understand what applications work best with line scan, and with that, what hardware we need to correctly implement these systems out in the field, as well as some other key factors to consider. So getting started, many of you may be familiar with the idea of an area scan. This is a rectangular or square region of a sensor that we're looking for given a two-dimensional area. Many of these are smart cameras, USB or GIGI interface, and typically we're going to be lower speed, lower bandwidth, and we have a lot more of a trade-off between our resolution to frames. And while many applications can be solved to this, there are certain ones that require us to have to look at line scan. And the line scan is essentially a very long and thin sensor. So instead of looking at a 2D array, we're looking at a very 1 or 2 pixel wide sized image. This allows us to go through much faster data and much more information quickly. So we have a lot higher data throughput, but because of that, we get a much better balance of price to resolution, meaning that we can get a 4K or even an 8K or higher sensor for almost half the cost of what you would need to implement that with area scan. The one benefit, as we'll get through this presentation, is that line scan, our frame rate isn't tied to the resolution. We're able to go as fast as possible without having to sacrifice that resolution, which is one big advantage as we start to look at some of the applications. Speaking of the applications, the big one that we see is a web or a thin film inspection. Now, many of times this can involve something from a tear or a coating defect or a delamination. This have been done with area scan in the past, but switching over to line speed, it really allows us to have a one-to-one correlation of where the defect is relative to where the line and images were grabbed. This becomes incredibly valuable when we have to process those images, and we can do this across any width really easily compared to that of an area scan. More commonly, we see cylindrical parts. So normally in a 2D, you might need multiple cameras just to see all around the can. Switching over to a line scan, we can rotate the can and line by line piece together and essentially flatten out an image that allows for little distortion for great image processing. That becomes incredibly important for being able to pull information from. But the biggest thing with this is your high speed and your high resolution. Any sort of applications that involve those are really good candidates for line scan, because we're allowing to take information line by line and piece that together very quickly. So when you have very large machines moving very quickly, area scan just is not able to keep up, which is why many of the webs are using line scan. Another more common one too is free falling. So if you have something such as molten metal or material, it becomes a lot easier to implement 1 or 2 line scan cameras as opposed to multiple area scan cameras. Textiles, especially for non-woven materials, is important for looking at different defects and rips, something that can be very difficult with challenging patterns or whatnot that you might see. These are only a small set of the wide variety of applications out there, as line scan is truly a versatile way to solve applications. Now, before we get into lighting, I just wanted to just kind of get everyone in the sense of where we're starting with from a camera side. And the way that we go about speccing out a camera is very similar that we would for an area scan. We're going to first account for what our minimum defect size is. This can be whether it's a hole or a certain area. And that's going to determine the resolution we need further down the system. Again, like area scan, there are monochromatic, color, and sphere options depending on what part of the spectrum your part needs to look at. But where we really start to differentiate is that our max exposure is really more determined by our line speed and pixel size rather than some more of the other parameters. Typically, on an area scan, you're setting a lot of the lens settings, and your exposure time is a resultant of that. Here, your exposure time is directly tied to what your line speed, and we'll go into explaining how that works out. So when we start to look at scan rate, this becomes very important because this tells us how much exposure time we have, thus justifying how much light that we do need. So in this example, we have a minimum defect size of 0.001 inch, a field of view of 20 inches, as well as a part speed of 100 inches. To figure out what camera resolution we would need, we're just going to take our field of view and account for a factor of 3 pixels. That ensures that no matter where the pixel lies, we're always going to get sharp images. We round that up as most line scan cameras are going to have dimensions in powers of 2, so 1K, 2K, 4K, etc. In this case, in this example, we would need an 8K sensor. And our size of pixels purely determined by our field of view based compared to our pixel size, which in this case is 0.025 inches. But where we really start to see the importance of exposure time is when we see how fast that we're going for something like this. And working out through the math, we see that we have an exposure time of about 30 microseconds. And that can be incredibly fast for many area scan applications, thus showing that, this is the big benefit. But obviously, when we start to look at very fast exposure rates, we're going to make sure that we're accounting for high amounts of lighting. And this is the big component of line scan applications, is making sure that you have enough uniform light to be able to saturate the pixels in such a short amount of window. Because that we're running so fast, we're typically going to leave the light continuously on, as else the duty cycle can get too high. Although depending on your application, you can strobe it, especially when it comes to switching wavelengths for different sort of UV versus visible. But generally speaking, line scan lighting we're always going to have on. And because of this, the light gets very intense and very hot. So it's important that we find ways to cool it, whether with air, water, or glycol, because we got to make sure that light is running continuously on, as opposed to an area scan where you might be triggering it every 100 milliseconds or something. The biggest component to look at for lighting when it comes to line scan is a high amount of uniformity. And this is especially important when we look for the direction of the material as opposed to the machine direction. We want to make sure across the whole width of material, we have solid illumination, as it can vary contrast level, and that can make it very difficult for image processing. Most line lights are going to have a uniformity spec at minimum of within 5%. So meaning as you go out, you're only going to lose within less than 5% of that overall light. When it comes down to applications that are further away or longer distances, that is when we have to account for collimated light. And this is incredibly useful when you have a light position several feet or even meters away from a given inspection surface. The collimation allows for that beam to stay focused and parallel more without spreading out, again, giving that high intensity at very far distances. And this can be accommodated through various means, through opticals, through lenses, but as well as film out there. And the big factor too is taking a look at the wavelength. Many manufacturers today are having packaging material doped with UV fluorescent material that allows them to see it, especially when it's a white on white material. Same thing goes for inspections that occur within the visible or even SWIR spectrum. We're starting to see a lot more in that area. And especially when we look at color print, having a high color rendering index is incredibly important. So if you're looking at something print, or if you're looking at the color of something, you wouldn't want your color of your Coke can to be Coke red as opposed to Campbell's soup red. And having proper lighting so that way your camera can see that is incredibly crucial, so you get that result. The big analog that we have with area scan and line scan is the fact that many of the lighting uh, formats and types and processes are the same. So just like with an area scan, if we had to illuminate a given size, we would use front lighting. And the same thing goes for line scan as well. But except instead of trying to illuminate a 2D area, we're really only illuminating a thin, quarter of an inch line incident on that surface. And that is what your camera and is going to be looking at as the material passes across it. In this case, some very generic examples is that with front lighting, with line lights, is you'll typically have an angle that's the camera with the beam pointing down. So that way, as the material is traveling through, you get basically every single part of that given web. When it comes time to do more dark field applications, we can use the same type of light, but just at a much lower angle. This is really valuable for helping us to pull out textured surfaces or structured features like you would see in a woven or a fabric material. A lot of the front lights do allow for this flexibility to be used in the front or back. But when we start using the front, there are applications such as battery inspection. So you can look at the anode and cathode layers and the separating layer as this machine travels by, and that becomes very useful for being able to determine where each layer is relative to one another. As I mentioned, backlighting is another way that we can use line light illumination. And generally speaking, it can more commonly, you may be familiar where you have a backlight shining in the same direction as a camera, but you can also, in some ways, be illuminating the part from beneath if it is transparent enough. This is really valuable for looking at holes in materials, especially large sheets of metal. Or even something like coiled steel, which is like for roofing materials. Um, and this gives a really precise accuracy on the size and placement when you're silhouetting. And a lot of the times that same front light that we talked about can also just be positioned back and be put in between two sections of a conveyor belt, allowing for that light to pass through the material. Which is very valuable, especially for space-saving applications where you may not have a lot of room to mount above or in front of the object. Another very common lighting type in area scan that you may be familiar with is something called a diffused axial light. And a diffused axial light, as you may know, is really great for when you have varying object to camera distance changing. So something like a printed circuit board becomes incredibly valuable because if you have different components, they're all going to get the same amount of illumination. This isn't the case if you just had something that was just a line light, as that different height will vastly change how much light is being able to illuminate that given surface. So while a lot of this uses a beam splitter to basically throw off the light in 90 degrees. And while a DAL is more commonly square, there are variants that are more linearly based. So instead of having an area that might be a 4x4 inch, the line scan variant is going to have a very narrow, maybe a 1 inch or a ½ inch strip by however long the web is needed. We see this a lot, like I said, with the semiconductor industry, to be able to really cut down that glare, and it becomes incredibly crucial to be able to do that. Similar to diffuse, but another more common configuration is people might be familiar with is dome lighting. Now, unlike diffuse lighting, which is really on axial lighting, dome lighting is highly diffused, highly lambert, which is really great for minimizing shadows on an object. And the way that this is done is that an LED array is positioned on the sides or on the edge, shining up onto a highly reflective surface, and then the light comes incident down. So you get light coming from all directions, or this sort of cloudy day effect. This is really great if you ever think of something like a golf ball. It becomes really valuable to be able to look at all that without the shadows. For line scan, it becomes very crucial when we're looking at pharmaceutical capsules too, which can be usually very reflective, very shiny, kind of half transparent materials. And that's something that being able to position these, if these were on a line getting feed through, is kind of take an image of one and not have to worry about that and get nice lumen, especially if you're looking at text on the pill or different things like that. Another type is definitely very popular with when you need to inspect optically clear objects, so such as acrylics or glass. There's configurations of lights that use dark field backlighting, which essentially shoots the light at a very low angle but a very narrow beam, and that really allows you to see very subsurface defects that you really couldn't see from front lighting, but you're taking advantage of the technique of using dark field. Dark field, is very, for those of you in the area scan, is very akin to something like an off-axis ring light. This is kind of in its own category, but still very valuable, especially for those in the glass acrylic manufacturing industry. Now, in addition to lights, we also just do have to mention some of our encoders and hardware that we're needing to properly implement this. As I alluded to earlier, because our light is continuously on, we're only going to be triggering our camera, and the only way we know when to trigger is using an encoder throughout the system, which ties into the line speed with your camera rate, allowing to make sure that no matter what, you're always getting very square pixels. So even as the machine speeds up or slows down, you don't have to worry about getting an over or underexposed image, because because you're leaving the light always on, you always have the same amount of light. So you're only changing your window on how large or small your exposure is. But because of that, mounting becomes incredibly important. And especially when you start to see multiple line scan cameras stitched together for very large webs, alignment is a lot easier compared to a 2D because area scan, because you have only one dimension that you have to line up, where 2D can be very challenging, especially the more cameras you add. So it's important to really have good mounting, especially in considering the angles of your lighting to your camera. As we saw earlier, having a much lower angle certainly can help pull out textured and features with geometry, but also can take away from some of the overall intensity. So it's important that you align those angles properly so you're getting the results that you need for your application. And like an area scan, we're also going to look at triggers and photo eyes to make sure that we have that system information so we know when to trigger our light and camera system. And speaking of lighting, they do have controllers for lighting that can also work with line scan. These can be variants from, in applications that are going much slower. These allow you to do control that strobe, where you do have you can run it at a duty cycle with a slow enough line speed, or even just intensity control for when you might need to dial it down, or if you need to switch between different wavelengths. There are many times where there's an application when you'll have one color of a product coming down a line, and that's going to use white light, and then you're going to have a different product, and that might have to use a slightly different light, or it might be having a product with UV fluorescence. So having that controller tied into a PL system is really crucial to be able to do that switching, especially do that switching very quickly, given the speeds that some of these have to run at. And again, because we need a lot of light, because our exposure window is so small, we do need to just account for some PC hardware that can handle that high bandwidth, just to make sure that we are not dropping any frames, or we're capturing all the information that we intend to. So when this all comes together, what we're looking at is something like this. This is a small snippet of a very basic line scan system. As you can see, we have our camera as well connected to our computer system. And you can have a light depending on, positioned in the front or in the back. If this was just looking for a tear, you might want to do some silhouetting in this. But ideally, this is what the basis of a line scan is that with a light continuously on, we're exposing one line at a time and then we're compiling these lines to create a frame, and that's what you're seeing on the camera output side. And for example, this is why typically your field of view is typically going to be the same width of your web, which is why also if you had a 20-inch web, you would ideally want to use a 20 to 25-inch length, so that way you have a nice illumination across the whole edge. And when you tie in the encoder, that allows the machine to know where that defect is in real time based off of a map of the whole web. So we can easily identify later down when we go to process that where that defect was taken from or what part. But no matter what type of defect you have, it's important that you consider what lighting has, as that can vastly change what contrast you have, especially given the environment that you may be operating in. If there are overhead lighting or if there's other indicator lightings, it's important to account for that when we're even looking at lighting, because we want to make sure that we are able to give as much light for the camera, because truly the faster that we can run the line, that's a higher throughput. And that really comes down to having a higher intensity light and be able to sustain that for a long period of time, which is why it's crucial to have really solid lighting for your line scan applications. Now, as we're getting towards the end here, I just kind of want to go over a little bit of a summary of what we talked about today. And that includes how line scan is a great way to unlock these solutions for these very high demanding applications. We're seeing a lot of development in battery inspection, and a lot of, with COVID, a lot of pharmaceutical packaging needs. Line scan becomes a very good way to solve these applications, and it does it because they're incredibly versatile. Depending on what web or material you're looking at, you can really find lighting to pair with your camera system that can account for any type of situation that you might find yourself in, whether you're looking at something very diffused or you're looking at something with a lot of surface defects or a lot of texture to it. It's important to have those options available in line scan, just like with area scan, because no two applications are the same. So having your options with lighting make sure is that no matter, a lot of applications can be brought from area. And even though you may have to have a slightly more hardware, at the end of the day, it does become a more cost-effective solution, frankly, because there are less pixels on the camera and less LEDs on the board, allowing for a really nice solution, especially when you get to increase the throughput of the machine, if you can increase that exposure time. So that's why at the end of the day, lighting has to be considered not only for area scan applications, but line scan as well. And lighting becomes so crucial because without it, you wouldn't be able to get the enough light and the amount of window that you would need. And again, I'd like to thank everyone for attending. And I think, Jacob, we have a couple of questions. If there's a chance I don't get a chance to get to your question, feel free to shoot me an email. But again, I'd like to thank you for attending and have a great day.
Austin, thank you so much for shining a light on line scan imaging. You basically stole my script from me. I'm too going to remind everyone in the audience that if you haven't typed your questions and your comments into that chat box, you'll be reached via email at a later date. Austin, I have to ask you, how important is a systems integrator for line scan applications?
So system integrators are really great, as they can really, depending on your level of expertise with line scan, they can really help walk you through the components that you need. Depending on what your application is, if it's something pretty, just looking for holes, you might be able to use your company's internal resources to do that. But there are some fantastic integrators out there who really can understand how to bring together your machine speed, your lighting, and your cameras to make sure you're getting that good images. They're a very, very valuable partner. So it really depends on your level of comfort, but it certainly does not hurt to reach out to them.
To kind of build on that a little bit, would you say that an encoder is required for a line scan?
For the most part, you do need the encoders, as without that feedback, you're not going to be able to have a lot of tie into the machine of how fast or how slow you're going. That becomes very valuable because you always want to make sure, no matter how fast it is, you're having these square pixels. If you speed up and you start having quicker exposure times, you're going to be underexposed. If you have longer you're going to have darker images. So that kind of keeps everything in sync. Think of it as like a clock. Although if you're just looking for something basic like holes and you don't really care for the size, or you just want a simple presence or absence, you can sometimes keep your machine simple, and you may or may not need an encoder. But that would be, again, a perfect example of why you might want to reach out to an integrator.
Awesome. Very good point. Would you say you can get more intensity by strobing the line light?
So yes, you can, but it does come with its limitations, given that you have to account for the duty cycle, or basically how much the light is on to compare it to how much the light is off. As I mentioned earlier, applications where you have to switch wavelengths, certainly where strobing can come in handy. But you can definitely get that more intensity, but you do have to factor in that duty cycle. Typically, landscape applications are running so fast, your duty cycle just would not keep up and you have to overheat the light. But I have seen applications where you can get that more intensity, and that's also where controllers come in handy too.
Awesome. We have time for one more question, and you just kind of hinted at it there. Would you say a controller is absolutely needed for line lights?
Yeah, I mean, like I said, it really depends. I would say so many applications are different, and
Mhm.
uh, everyone's um, needs for a certain solution can vary. But for the most part, having an advanced PLC system, power management, is crucial to be able to control that intensity of that light. Having controllers just kind of enhance your ability to interact with that light and really get the most out of your given system.
Austin, thank you for taking a couple minutes to answer some questions. I'd like to remind everyone in the audience that this session is hosted by us at Photonics Media, and we hope you're enjoying the 2022 Vision Spectra Conference. Austin O'Neill, thank you so much for presenting lighting considerations for line scan imaging.
Thank you.